Thank you very much. So, before lunch, we'll go now. The topic is connecting dissimilar materials for crash applications. So I will touch now some of the most complex parts here, which we have in the simulation with radios and open radios. So thanks to the speaker before, so he showed already what's possible with open radios. So it will be a little bit complex, so luckily before lunch, this is good. So the first 3 hours I will explain you the equations, then we will do the test. Okay, now I'm joking. Okay, I did it together with Stefan Kollink, which is here. You heard his talk before coffee break. And it was also together with some research projects, which we did in Germany, and some European funded projects with automotive industry, but not only. So you will see some interesting topics. We will touch again materials, because dissimilar materials means different materials, not only steel, failure criteria, connection elements, connection modeling techniques, reality versus virtual world, which means simulation in radios and open radios, contact interfaces and so on, failure of contact interfaces, cohesive zone elements, so all this beautiful nonlinear stuff, which you can imagine, we will talk a little bit about. Okay, safe harbor statement, so I will not read this because we are a public company, I have to show it. You can read it somewhere in the coffee break. This you already saw, so I will skip it. So our vision at Altair is computational intelligence will drive innovation for a more connected, safe and sustainable future. So this is what we want to now democratize, and what we did with hypermesh, which you saw before, but also with radios, OptiStruct, implicit solvers, and explicit. And even with radios, you have the commercial version as well as the open sourced version, which you can use for free without any license features. You can even see in the source code how radios is coded. I will come to these points in a few minutes. Okay, let's get started. First, a little bit theory, the implicit part, which is, for example, OptiStruct, Nastran, and so on. All the implicit solvers are working in this way, and this is the heart of it, where the stiffness matrix, I will go my pointer here, is times the deformation is equal to the external forces. Once you reach this equilibrium, you are fine, and you will have your global solution. Perfectly fine. For implicit works, if you are lucky in one step, you will get the convergency, equilibrium, everything is global, solution, perfect. So, but if we go now for a little bit more complexity and compare the CPU costs, what is our lessons learned? If the complexity is increasing, because we add non-dynamic, non-linear stuff. So the costs are also increasing for these kind of simulations here, what you can see here. Whereas if we switch to explicit, the opposite is the case. It is usually much more performant here if we are in the nonlinear domain and the complexity is high. The explicit costs are decreasing, which means higher velocity, nonlinear material properties, fracture, separation of parts, which is even not possible in implicit, or not so easy. Anyway, the world today is not black and white like this, so it's kind of this. The implicit solutions you can use here for this. If you are in static, elastic load cases, implicit is perfect. Plasticity, slightly, so buckling, even less. If the velocity and dynamics are increasing, it will become more and more difficult to use the implicit solvers. We're switching to explicit solutions. For sure, times are changing and solvers are evolving. So now it's not black and white anymore. We have intersection area where it is not so easy to distinguish what kind of solution should be used. Therefore, both solvers are now evolving. The implicit solver like OptiStruct is becoming more and more features of the explicit solver. So you can even now do drop tests with OptiStruct, so it is possible. Whereas explicit is also going to this region where it is usually very costly to do static simulations for an explicit solver. Okay, let's go now to our use case, why I'm today here. So what is my use case is typically this, crash. So, and this is where I would like to spend a few words on because it's quite challenging topics which I want to address today. Okay, let's go anyway again back to the theory. What is this equation which we are playing now? So this guy is called the equation of motion, where we have the mass times acceleration gives a force, damping times velocity is a force, stiffness times deformation is a force, is equal to external forces which are time dependent. They can also be zero. If they are zero, you have free fall, for example. So, and what is now the definition of an explicit solver? So this is our guy. We start from time zero and we are looping over external forces, internal forces which are based on, in the material routines, for example, strain rates, go to stress rates and assemble to stresses and so on, continuum equations, next time step. So this is a loop in time. What is the final criteria for this? Where does it end? There is no one. Therefore, it's called explicit. You have to define explicitly the termination time. So here, the solver does not contain any final criterion. You define it explicitly after 100 milliseconds, for example. So solver stop. Wherever, independent if the problem is already solved or not, the solver stops. For sure, you can do restart and continue and so on, details. And this is again the equation of motion, which we are solving with the explicit solutions. And this is now the reason why we developed in the past radios. I will go to it in a few seconds. And from radios 2 years ago, we split out open radios, which is now the development version for radios. So you, everyone, can take now the source code, the entire source code of radios on GitHub, compile it, or you can even download a pre-compiled version and use it. No limitations. There are some differences. For example, encryption is not included in open radios. Why not? Because it doesn't make sense. If you have open source software and the material models require the values, you can go inside and add a small print and you will get the value. So which is and we have to protect the existing encrypted models like dummies, barriers, or many companies are still using their encrypted material cards because as you saw in the previous talks, creating a good validated material card is very, very costly, time intensive, and you need a lot of tests. I will come to this point as well later on. And therefore, if you are deal with your whatever partners or other companies, you want to protect your IP, or the others want to protect their IP. Therefore, they have to use the commercial version of radios, where it is possible. So, okay, let's go to the roots. What is radios? So I took this presentation, this slide from Paul Dubois, who presented it last year at our Open Radios Users Day in Aachen, here in Germany. And he is showing now the family, the Dyna 3D family, which represents the solvers created by the Los Alamos laboratories in 1976, which means a few years ago. So where here easy, created PEM crash, and then Mechalog separated with radios. Here on this branch, you can see Alice Dyna. Here you see Abacus explicit. So this is the old Dyna 3D family, which means the basic theory for all these solvers is the same. And you can do the proof. You can download from GitHub some, let's say, tensile test models up to fracture, compare, which is in Alice Dyna format, the star keyword format. And you can run it directly with Alice Dyna and with Open Radios without converting. Do not change nothing. Just use the Alice Dyna model, run it with Open Radios, and compare the results. And again, don't trust me, do it by yourself. Okay, these are the history. Later on in the history, in 1991, the first car-to-car full vehicle crash was done by Opel AG using radios as well. So this is an industrial proven solver, which is created by for the industry, and again released 2 years ago also as open source. So it is not an academic solver, it's an industrial solver. Okay, now let's go into some projects which I can show you. For example, the Light E-Body project, which was funded by the German administratives, and some companies were involved here, like Ford, like Volkswagen, like other companies who are producing materials like ThyssenKrupp from steel or Dow or hydroaluminium. So different materials. And these guys said, okay, we want to create a virtual car where all our materials will be used. So they started with just pure geometry, did some optimization with OptiStruct, and then started to create an FE model, body in white, and then later on a full vehicle, which is synthetic vehicle. It was kind of a merge of an VW car and a Ford. So you cannot see it here, but if you do the silhouette, you will see this is kind of Volkswagen Golf and Ford Focus, which is kind of merge and a hybrid vehicle. And then for sure we did some tests. Euro NCAP front crash, side crash. So you see the individual crash cases below. So which is here. The offset deformable barrier, pole crash, moving barrier, so deformable side crash and rear crash, and some other scenarios which we investigated here. And the main point what we used then was how to bring all these different materials together, because it's a multi-material mix which we have here: steel, aluminum, polymers, composites. So most of these materials are used in the typical cars today. For steels, we have different grades: mild steel, hard, high-strength steel, ultra-high-strength steel, and so on. Composites were used also in different areas. Aluminum alloys, different ones. How to connect these different materials, because they are used in these areas here, where you can see the individual material mix. And then some parts are made of polymers, plastics, and aluminum, composite, and so on. How to connect, for example, steel with aluminum. These metals don't like each other, so you cannot weld them. So you have to use different approaches. Or whatever, composites and metals, they even also don't like each other. And here, for example, the B-pillar, we have different materials: aluminum, steel, composite. How to connect these materials? This was really big question. And from real world, we know joining techniques like point joining, spot welding, screws, clinching, self-piercing rivets, and so on. For lines, laser welding, bonding, and for area, also structural adhesives, and so on. So here, spot welds, for example, from reality. laser welding lines. So again, self-piercing rivets where you can connect dissimilar materials. And all these connection technologies were used in this project. So basically very often also bonding using adhesives, welding so for these kind of connections. For dissimilar materials, it's working pretty well, depends on the area. So many different techniques were used here within this project. This is what reality shows what is used in reality. Okay, now let's go to virtual world. What can be used now in FE simulations? So from the past, joining technologies in the past is using, for example, rigid body, which can connect whatever it is with an infinite stiff connection method, which is just an equation. Much better. So you use, for example, here bolt, which you have here one spring. You can even add pretension forces for bolts and then connecting to different surfaces and so on, which can be completely rigid or deformable here, whatever. So now, then, in the past where the mesh size was 10 millimeters or larger, which means 10 years ago or 20 years ago when I started using these things, for this large mesh, it is fully okay to add two nodes, connect them with tight contact interfaces and define a spring here which represent a spot weld or whatever, fully okay for large mesh elements. So because the force will be distributed on a large surface, everything is fine. Nowadays, today, the world is changing and our FE models are also changing. Again, in the past, also what was also used, common nodes for connecting elements, rigid bodies, beams, mesh independent, and now we are going to use also solid elements. Why? Because the mesh size is getting smaller. And if you have a very small mesh, let's imagine 1 millimeter square, and you apply a force to it. Force divided by the area is the stress, and the stress is increasing if you shrink your mesh. Therefore, this method is for typical applications today not useful anymore because the mesh size is so small. Smaller than 5 millimeters, I would only recommend to switch to distribute the force on a larger area with a solid approach. So, and how can it be done? For example, in HyperMesh or previously with HyperCrash or other tools, you create one solid which represents your connection method. It can be an adhesive, it can be spot weld, it can be whatever, self-piercing rivet, and so on and so on. Tie the nodes on the one side of the material and the other side to the second material. Everything is fine. This is the state of the art, creating spot welds, for example, today, which are represented by one solid. If the mesh size is shrinking further, which is the case, so then one solid is again not valid anymore. We have to split the solid into finer solids. So therefore, we are going to split. This was state of the art maybe 10 years ago. This was maybe 5 years ago. Today, we are going to this size of mesh, representing also the connection influenced zone, which can be heat influenced zone in case of spot welds. It can be whatever, some other connection methods like rivets or whatever, where you just shoot a hole through it and you have these initial cracks, which can act as crack initiation areas and so on, where you reduce maybe the stiffness here or add some damage to this area. And today we are in this phase, and this is how it was done in this project as well. And this will be in near future, we will go with this mesh size. The computational power is increasing. You saw some words today morning about HPC. This will be in near future, so I'm sure. Because today we are at this level, tomorrow here in near future we will do this like that for point connections. So now let's go for adhesives, because we have to deal also with testing. First, getting the information by normal tests, normal loaded, shear loaded, and also peel. For adhesive, the peeling is very important, because here the areas are rotating, and we have this peel effect like you would peel a banana. So, and this is very critical also for adhesives. So how to test it and how to model it. So we did it also with Dow, Betamate, and connected also mesh independent this peeling layer, adhesive layer, which is here, was connected to both surfaces, mesh independent, using a tight contact interface, which is very nice and works pretty fine. If you go and bond adhesive between two metals, plain metals, without any coating, without any paint on it, and so on, which is for testing the adhesive, it's perfect. For reality, we will see. Okay, how to now to deal and to model this, all these materials and failure criteria for real applications, because in reality you do not have naked steel. You have always KTL surface or whatever paint or whatever coating on your metal, then you apply adhesive and so on and so on. So in reality we have this kind of situation. So here we have material 1, here we have material 2, which is a different kind of material. This can be, for example, a metal, this can be a polymer or composite, whatever. Or steel and aluminium, same issue. And then we have coatings, and we have the adhesive. And then we load the structure in this way. This can lead to different fracture patterns. Cohesive failure, for example, which is here. Adhesive failure, which is here. Coating failure, which can occur here, and the material failure which can occur here. So we have to model all these individual materials and failure criteria and to test them separately to have a validated model. So this is normed in the standard ISO 10365, so you can read it, how it is defined. And we did these tests. And then we also did some material tests, which were quite dynamically loaded structures. For example, here, cast iron in this case, different velocities, different shaped test specimen for getting more information about the failure mode. So this tensile dog bone test is not sufficient anymore. We need more information on bulky materials using the cylindrical tests for shear tests, plane strain, compression tests, biaxial tension test with this punch test, and so on and so on. Sharp bending tests to determine and to have more information about the fracture models. For the material cards, just different velocities from a tensile test were used here. So where's my here, strain rate dependence on metals in this case was obtained. For polymers, it's even more valid because polymers are definitely very high affected by viscosity, which means different loading velocity. For metals, it depends. You cannot see it on the metal, you have to test it. Some metals are highly strain rate affected, some are not, or do not show it too much. Which one is which one? I don't know. It must be tested. Okay, for getting the material card, you do this tensile test, which is the first approach which you do for fracture. in the past, so this beautiful fracture limit was obtained or put in the material card here, radius or elastine or PEM crash, all the same, and people were happy. So maximum plastic strain add to the material card, and it failed once this plastic strain limit was reached. Very nice, beautiful, simple to use. You need one test and you input your value directly from the test. But there is of course also a drawback. Flat line in the failure curve versus a triaxiality diagram, which means it's not physical. What does this mean? Here, the maximum plastic failure strain is this one. Flat line, if you compare over triaxiality, which means the ratio between hydrostatic stress and von Mises stress, which helps you to distinguish about the load case. Compression, shear, tension, because the materials behave different if you load them, for example, in compression. Usually, the materials can go with a higher strain until they fail. Whereas in tension, they are critical. Shear can be somewhere in between, and so on and so on. So the reality looks something like this. So what is obtained from reality? Material behavior to fracture depends on how it is loaded. For compression, usually not so critical as for tension. Shear can be here, somewhere in between. Most critical part is usually the plane strain load case, and so on. You can use for this, for example, some analytic models which exist, like Johnson-Cook failure criteria, which gives you this kind of shaped curve, which is better than the flat line. It distinguishes between failure in compression versus failure in tension, which is good. Or even more complex one, the modified Moore-Coulomb, but try to fit these beasts. So this is such an equation. It's a challenge. Yeah, this was developed by some funny guys, which add here some functions like SEC from whatever. So it's just 1 divided by cosine, but SEC sounds better. But it describes the reality much better compared to the flat line for fracture. For sure, we developed also a new failure model, which is bicquad, which is even simpler, 2 parabolic equations with intersection point in uniaxial tension, so which gives you the much easier way to use it. Just enter here the failure strain for fraction in case of compression. Here you add the failure strain for shear. Here from the beautiful tensile dog bone test, for example. Here is plane strain, and here is biaxial failure, which you can use this kind of test, or a punch test, which means a sphere through a plate, whatever. So there are different geometries or test methods here. Just ask your test lab, and then you can go for validation. So this is quite user-friendly, even if you do not have, because here it requires 5 different tests with different geometries. Who is doing that? I would say almost no one. If you are lucky, you can do the tensile test. So then you are already lucky. So which means we had to do it simpler. And we simplified it. So we did it much simpler, where you can now forget the compression test, shear test, and plane strain and biaxial. Use only the most used tensile test. Keep these values to 0. And set a material flag here, which provides you an internal database for some material families, where we obtain the values from different research projects, and they act already very, very good. So you don't need to do these kind of very, very enhanced tests. There is a small material database included in Radius, which you can already use with predefined values. If you are happy with them, use it. They work surprisingly well. If you are not happy, you can fine-tune it by adjusting The entire curve, you can tune it with this parameter, which you obtain from the tensile test. So, and the entire curve will be shifted. And the shape of the curve is defined in the material flag, which is behind this flag. You can see it in the manual or ask me in the break so I can explain it to you even more. So this is for the failure criteria for base materials, like metals, whatever. So let's go to the next one, cohesive adhesive failure. So here we worked very close with Dow, which is now DuPont. So they were acquired by DuPont or merged. And we used Betamate. So we tested this adhesive in different ways, how it behaves. And then validated our models. First of all, modeling with cohesive zone elements. And the adhesive layer can be very, very short and small. You can now also model it with a high, whatever you want, and apply a value for the true thickness. Why? Because you model this adhesive with a solid model element, but it is not a continuum mechanical solid element. It's a trick. It's just a cohesive zone element, which can have a volume of 0. No issues. It has only 4 integration points in the mid-plane, so which act like 4 springs. So very simple approach, which exists in any solver, in Altair, in Pemcrash, Abacus, Radius, of course. How to deal now with the fracture criteria? So we developed an equation for it to deal with fracture in different load scenarios and the symmetry value, which helps to distinguish the peeling force. With rotation of one surface against the other surface, you see a reduction of the normal failure force. And this is what we figured out in this research project. And now you can use for peeling this kind of test and fine-tune these values here. So this allows you now to catch the peeling effect in addition to failure in normal direction and in pure shear direction. So this is the influence of beta, the exponent. You can go to this kind of shape from more or less decoupled to fully coupled. So you can do it, fine-tune it by different tests. As well as the fracture, the failure is described with the same equation but different values here to define the failure surface here. And between initiation of failure and full fracture, you have softening, which you can also define until the full terminal failure for these adhesives. For sure, you have to do some tests, which are, for example, this KS2 tests, where you see here now in red the experiments and the blue line is the validation for all these tests here, and we are in a pretty good agreement here with the tests. And now go for validation of a more complex structure here, this T-join, which we did also and validated it here in a pretty nice way. And this picture is showing also the reality, the real part, which the adhesive by this load case is failing here in this area. But again, coming back, what we are using in automotive is not naked steel. It's covered by whatever, KTL surface, paint, or whatever. So we have to consider this as well, because it's there. And what we see here, pictures from reality, where you see failure of the coating here in this area here, where it is teared apart from the metal below. So once we have loaded it very highly. And this pink stuff here, this is the adhesive. And here we have the paint, the coating. And here you have the naked material, metal. So we see failure, the coating failure here in reality, real tests. How to model it? The surface thickness of coating is very, very thin. So even for today methods, we cannot model it with elements. So we can use tight contact interface with definition of failure here in normal direction and shear direction. So you add a tight interface between two layers of elements which do not have the same mesh, different mesh. And in between, you model your coating with an interface. So once you do that, you have now the possibility to model material and fracture for base metal, material, must not be metal, whatever, polymer, the adhesive, and between adhesive and your material, the coating by contact interfaces. So and now let's do the validations. First, fracture is applied only in the metal, not in adhesive nor in coating. And we see once we load this is the virtual, the test, the FE simulation done here with radios. We see only fracture in the base material. Why? Because I applied it only for the metallic part, not perfect adhesive, perfect bonding, which is not the reality, but just for tests. Now I apply failure in addition to the metal also for adhesive. And I see here my elements, which represent the cohesive zone elements for adhesive, are disappearing, which is much closer to reality. And now but the painting is still perfect, the coating. And now let's apply also fracture in the coating. And now I can see some elements are still not broken for the adhesive, which means the bonding has failed. The contact interface, tight interface failed, and I still hear the adhesive is still gluing on one part, on this part or here, which means the failure occurred in the paint. So and this leads me to the end, more or less. Now, if I do some pre-sneaks for Michele's presentation, so these are for engineers simulation and post-processing methods. For management, they prefer something like this, high, more sophisticated rendered pictures. So these are renderings from FE models, simulations. So photorealistic renderings, which you can also do with Hyper-V, but Michele will show a little bit more features on that, hopefully. So which is already possible to do photorealistic renderings for your management. They will appreciate that. Okay, coming to the end, summary conclusion. So Radius offers many predictive material and failure models. Still further, so we increased even the speed of development by open sourcing it. So now the universities, like what you saw today morning by Professor Collins and others, they are started developing, enhancing it, because they have the entire source code without limitations, which you can also use. Damage initialization and visualization possibilities are already implemented because it's an industrial solver. Advanced interfaces for modeling coating surfaces with failure, in addition to classic penalty contact interfaces, are available, and so on and so on. Anyway, there's still a lot of need for further investigations and structural behavior of coated metallic structures using adhesives, and also for new materials, new whatever methods for modeling failure and all the other nonlinear behaviors. So here I would like to invite you, participate here and use your brain, help us developing further this solver. You can use it for free as you want. So thank you very much for your attention.